Welcome to the Bytecode, where we look at smart contracts with the people who wrote them. I'm Mirosh Shafu, and today's episode is with Farhaan. Farhaan, thanks for taking the time, man.
No worries. So hey everyone. So yeah, my name is Farhaan. I'm the team lead for smart contracts here at Maple Finance. So yeah, I guess today we'll be covering the Maple Finance smart contracts, give you guys a bit of an overview. A lot to get through in an hour, but it will be exciting nonetheless.
That's exactly right. We're gonna go through Maple Finance today. We have some super interesting topics. A few of them I wrote down. So we're gonna look at invariance testing, how you guys are gonna do the operational stuff. There's a super interesting bike check mechanism to make sure you actually deployed the same stuff, or if something changes that for auditors and stuff. And yeah, we're gonna go through some monitoring as well, some health checks that you guys are do after deployment. So yeah, why don't you briefly introduce Maple Finance and then go through the architecture?
Awesome. Yeah, you guys can probably see like the architecture diagram on the screen, but yeah, let's do a brief intro of Maple. Maple Finance basically provides on-chain capital debt market infrastructure. We're also now branching out into managing pools ourselves as well. But to give you like a bird's eye overview, essentially we're bringing together three parties. So you can see them denoted by these circles on the left. So we have liquidity providers, we have a pool delegate, and we have a borrower. So essentially, we want to match liquidity providers with borrowers because the borrowers will borrow at some interest rate and then pay that to the pool, and then the liquidity providers will obviously be paid for that. But because we're often dealing with like real world assets or over collateralized borrowing, under collateralized borrowing, we actually support like any mechanism here. Usually people associate us with just under collateralized borrowing, but that's just like one niche. Like there's other things that we do as well. Like we're providing on-chain treasuries as well. So the pool delegate is the underwriter. So they're the ones kind of managing who can borrow the funds, who's allowed to actually be a liquidity provider as well, especially if we're using a permissioned pool. So we support both permissioned and unpermissioned pools. So it's like complete flexibility in terms of like what is like the scope of the pool. So to give you two concrete examples, so you can get an idea of like use cases. So one that I alluded to is treasury management. We call it cash management. So essentially what's happening is you have KYC liquidity providers. We support US, non-US investors. So they provide funds into a pool. The pool delegate in this case would be Maple Finance. And there is one borrower in this case. So this is kind of like a unique example of our pool system. The borrower in this case is Room 40. They're a hedge fund, so they use an SPV to basically borrow funds from the pool, and they go and directly buy treasury bills. So they buy treasury bills at whatever the rate is at the time. So let's just round it down to like 5%, but like 5.5%, for example. And then they would take a small fee from the pool as like how they're earning money basically. Maple Finance will take a small fee on that, and then like 4.75 to 5% ish then gets paid out to LPs. So then, because the borrower has this on-chain loan, they have to make payments at a regular interval, whatever the agreed upon loan terms are. So let's say like a 30-day payment schedule. So every 30 days, they would pay any interest due. And that's just going to liquidity providers. And then we can get into withdrawal mechanisms separately. But that's like one use case. Another example would be our pool with Accrue. So Accrue is the pool delegate in this case. What they're doing is they're underwriting loans to a borrower called Interio. What they do is they give financing for tax receivables, so IRS tax receivables. So what that means is there's a company out there in the world that is going to get, let's say, $1 million back as a tax refund, but they're not going to get it back for another 6 months, say, for example. So we can provide liquidity via Interior directly to them. So let's say we pay them, $950,000, then that $50,000 is like the profit that's being generated, i.e. the yield. And then, yeah, that gets paid into the pool basically. And that's like another example of like a real world asset situation. And I guess a final example, which is a bit closer to home, which we just launched yesterday, is another pool called Maple Direct. So Maple Direct is managed directly by us. We're doing over collateralized lending basically. So you guys are probably familiar with what happened last year with like the likes of Celsius, etc., where they were providing this borrowing service as well. But everything went like under because people were rehypothecating. There wasn't transparency. Someone like didn't know, oh, they borrowed from Genesis and then they borrowed from Celsius, and one person could have borrowed with the same funds from like 10 different providers. What we're doing here is using our on-chain infrastructure to do transparent lending on-chain with this now. So yesterday we put out our first loan for 75K to this borrower, and the borrower put up collateral of Bitcoin, which is they put up like about 250% collateral, so about 10-ish Bitcoin or 7 Bitcoin, if I'm not mistaken, against 75K. So it's over collateralized, and we're using an on-chain we're using a custodian, like BitGo in this case, to do this. So that way we can support native assets like Bitcoin, because of course you can't have native Bitcoin on Ethereum, which is where we're based. So yeah, that's a cool example of how we're using on-chain infrastructure to do this transparent lending now. Because now on-chain, the loan will say, yeah, they're borrowing 75K. The website will give you the information of like the custodian and how much is being collateralized and by what, and that can't be rehypothecated now. So yeah, lots of moving parts. Our system is quite configurable, and yeah, we do support a lot of use cases. So yeah, capital debt market infrastructure. That's the TLDR of Maple, I guess.
Nice, very, very cool. And congrats for the launch, by the way.
Cheers. So shall we go over the architecture briefly so everyone can get an overview of what's going on? I guess the way that I will kind of start describing this is let's think about this like you're an ERC20 token. So let's imagine I'm USDC. What are the contracts that I'm going through, and how is this working? So we'll focus on the blue contracts. So the blue contracts are instances of an actual pool, and then we'll cover the factories in a moment as well. So me as a depositor that deposits
Farhaan, sorry,
USDC.
could you zoom in a little bit?
Yeah, sure. Is that better?
Maybe a little more.
All right. Yeah, I think because I don't want to lose the whole overview, but can you clearly see that, or a bit more? Yeah.
Yeah.
All right. All right. See. I'm a depositor. I'm an LP in this case. So what am I doing? I'm then depositing USDC. I deposit into a pool contract. Now this pool contract follows the 4626 standard because we do want to interop with the rest of the ecosystem. So I deposit funds into this pool. So now the USDC is sitting there. Now, how does a loan get given out now? We'll talk about it through the lens of an open term loan. The system supports two types of loans, fixed term and open term. With fixed term, upfront, you need to say when the end date of the loan is, basically, because you define it by the payment terms, like how long between payments and how many payments. So let's say, 30-day payment intervals and maximum 6 payments. So yeah, you can do the math there, how long the term would be. Or you do an open term loan where you say, hey, I want to borrow this amount and I'll pay interest every 30 days. And then I'll only pay back the loan when it's called. So that way, someone that continuously needs liquidity can have it. And then when we need the principal back with the interest, we can call it as well. Pool contract USDC goes in there. Now the pool delegate interacts with mainly the pool manager contract. So the pool manager you can think of as the central nervous system of the entire protocol. So you can see like all these interactions happening with the pool manager. So on the pool manager, you would have functions like funding a loan, etc. So what a pool delegate would do, that's underwriting the loan, would fund a loan. So let's say, imagine this loan is already created. So they would pass in the loan address, confirm the terms, and then just fund it. And then what would happen next is funds would get pulled from the pool via the pool manager, get sent over to this thing, what we call the loan manager. Now the loan manager we can cover as well when we go through the contract code, but it's a really interesting way that we've kind of developed to ensure that there is like a clear issuance rate in terms of the interest that's being paid out. So actually, let's draw this out as an example. So one issue we had previously is, so let's imagine a chart. So we've got time and we've got issuance. So and then let's imagine a pool has $1 million in it, and you've given out a loan for $1 million, and you've got 10% interest that you expect over a year, and a loan pays out every 30 days. What had happened previously is the issuance would be zero, as in the interest per second being generated would just stay static, and then there would be a jump. Suddenly, at time t, there would be, I don't know, like let's say 1,000 units of an asset suddenly paid, and then it would go flat again, and then boom, it would go up again. This is something that obviously you can front run and add like MEV risk, because now imagine, hey, I know suddenly there's going to be a big payment coming in of interest. Let me deposit into the pool because I get equal shares, because it's shares, right, that you get. So suddenly you'd be like, oh crap, like someone can just deposit and get a lot of interest suddenly and then like exit the system. So we didn't want that. So what the loan managers do, both for the open term and fixed term, is they smooth out the issuance rate. So it looks more like a linear graph like this, because essentially what the loan manager does is it figures out, okay, this loan is over this duration and I expect this much interest to be coming in over an interval. So, the units for this chart would be like, the issuance per second. So in this case, it'd be like, 1,000 USD per second, maybe. So that's what the loan managers are doing. So if we can zoom back in, I think we're at like 210. Yeah, so we've deposited into the pool. Pool delegate has funded a loan via the pool manager. It's gone into the loan manager. The loan manager does the calculation to figure out, how much the issuance rate should be, what to expect, sets up the loan parameters, and then gives the funds to the loan. So now the loan has the funds, or actually in the case of open term loans, the funds gets directly sent to the borrower. So that's kind of like a brief view of how the ERC20 token, or USDC in this example, goes through the system. So let's zoom back now and what are the other elements in this system. So to create a pool, you go through this pool deployer contract. So pool delegate multisig would call, so let me use a slightly less thick background. Let's use this. So yeah, the pool delegate would call the pool deployer, and the pool deployer would then call all these factories to deploy a pool. So you can see the pool manager factory gets called. It ends up deploying a pool manager, pool factory. These are actually combined in reality. Withdrawal manager factory deploys a withdrawal manager, fixed term loan manager factory, fixed term loan, open term loan manager factory, open term loan. So you can see we've got lots of factories. So these factories deploy proxies. So we use proxies extensively in our system. So all these contracts that I just talked through in the blue, these are actually unique instances of proxies that are then pointing to their relevant implementation. And by using all these different factories, we can actually support different versions. So say we just want to go update our open term loan, the implementation for it. So let's say it's on version 100 and we want to update it to version 200. We would just deploy a new implementation, register that implementation on the factory, call the upgrade function on the implementation, which will then upgrade the proxy to point to the new implementation via the factory. So yeah, proxies are used extensively, and yeah, we're using transparent proxies basically to do that functionality. So that's the key essence of the pool and the journey that different ERC20 tokens go through. Then there's a few things we have for security purposes. So we have this contract, which you might have seen up top here, Maple Globals. So Maple Globals holds a lot of information like who is a valid borrower, what are valid pools, it activates pools, it's got security functionality like circuit breakers, where we can pause either the whole protocol, a specific contract, or even a specific function. which I think is quite cool. So we have like super granular circuit breakers because of Maple globals. Um, and yeah, you can see there's like a governor multisig that manages the Maple globals contract. The Maple globals contract is actually also a non-transparent proxy. As in, it has the set implementation function on the proxy itself. And yeah, and this is like one of the few different kinds of proxies that we manage as part of our system. So I think yeah, that's a high level overview of the system. I appreciate there's a lot going on, and it's hard to maybe grasp initially, but yeah, that's the TLDR of the architecture. I guess yeah. Do you have any questions that might be useful for the viewers? If not, then we can get into the code.
We should definitely take a look at the Maple's Global's circuit breaker logic. This is super interesting as well, I think.
No, for sure. All right. On that note, let's get into the code. And actually, yeah, just because you mentioned it, let's go into Maple globals. So there's a few things going on with global. So actually, maybe let's talk through how we structure our repo. So the repo that I'm covering is Maple Core V2. This is public, so anyone can see our code. You can see almost using 100% Solidity. We are heavy Foundry users, big fans of Foundry. I think we've been using it almost since it came out. We've been working with them to kind of help refine some features and stuff as well. We worked with them to help develop like the invariant test suite as well. So yeah, big Foundry shills over here at Maple, for sure. And yeah, otherwise, we're just using like bash scripts to kind of help us out. But yeah, mainly Solidity. But yeah, let's go a bit over like let me cover that and make this slightly bigger so you guys can see. So this is our mono repo. So what we do here is we import different modules and put it all together and do integrate like system-wide integration testing in this repo. So an example of a module is all the logic to do with pools, for example, like that we have over here. This is its own module. Everything to do with the withdrawal manager is its own module. Everything to do with fixed term loans is its own module. Everything to do with open term loans is its own module. Maple Globals is its own module. So you can start saying, yeah, there's a lot of moving parts and modules in the system. Everything to do with liquidations is its own module as well. So let's go through the module. So we have an address registry. So this is kind of like where we keep all our on-chain addresses. We also have our own ERC20 implementation. So one thing you'll note is we don't actually have that many external dependencies. This took inspiration from like Soulmate, OpenZeppelin, and DSS. But yeah, the only external elements we have is basically listening to a Chainlink price feed, which we rarely do as well, and using Forge standard for testing. But that's kind of like a testing dependency. Otherwise, we have like zero external dependencies.
Okay.
So yeah, we have our own. Yes, sorry.
Question. So first of all, could you zoom in a little bit again? But the
Yeah.
question is why re-implement the ERC20, for example? Is there something you had to change, or what's the reason?
So it's just we didn't like the Open Zeppelin implementation completely, didn't like the Soulmate one completely.
Okay.
We wanted to take a bit from everything, and we are also quite particular with how we like format and read our contracts. So the way that we use like headers, like we use 140 characters as like the maximum length. The way we kind of just like organize storage variables, or even how we write out our functions, we're just like with formatting and everything, we're very particular because our goal is to make our code super legible. Like the priority is legibility, because we believe with legibility will come good security, to the sense that if it's easier to read, it's easier to audit, it's easier to internally audit as well, and to get a more intuitive understanding of what's happening in the code, as opposed to like having a lot of complexity. And because we write our own ERC20, we know what it's doing completely, where there's no like, oh, gotcha, of this specific function has this quirk to it of like some external library that we're using, basically. So that's also the key reason for it. Yeah.
Okay, makes sense.
So that's the ERC20, and then yeah, like I mentioned, so fixed term loan and fixed term loan manager are their own modules, globals, open term loan and loan manager, pool and withdrawal manager. So yeah, we've got this submodule system that we're using. So these are just Git submodules that you can add using, the Git submodule command. So Git submodule add, and yeah, the great thing about using this modular system actually that we find is um, we can support different versions of contracts very easily. To say we have open term loan where it's got a specific implementation. So let's say this Maple loan contract, so you can see it says V1 for this open term loan. So let's say we create a V2 with different functionality and we want to test both within our monorepo. We can just create a submodule where we say, open term loan V1, git add the submodule at that specific commit, and then do the same for V2. So that was like another rationale for why we want to use the submodule system, because we might have different implementations of versions of the contracts out in the wild at any given point, and we do want to test both versions at the same time to just check like there's no issues. So that's like another rationale to using the submodule system. But with that said, let's get into globals and show you that granular pausing that I was talking about. So let's take a look. So actually, let's go to storage variable, storage layout. So yeah, another thing I guess I can show you is how we kind of manage our proxies. So yeah, this is a non-transparent proxy. So you can see we use submodules within our submodules to kind of make our life easy. So this is our own implementation of a non-transparent proxy contract, where the set implementation function is an admin function that's actually on the proxy itself. I appreciate OpenZeppelin uses slightly different terminology. Their version of a transparent proxy, I think, is what we call a non-transparent proxy, and what they call UUPS is our version of a transparent proxy. Uh, so yeah, this might get confusing if you're familiar with OpenZeppelin, but here we're basically saying this has the set implementation on the non-transparent proxy. Um, so this is what globals utilizes under the hood. So let's go look at our protocol pause. So these are the main pause related functions. So you can see we can either pause the whole protocol, so via set protocol pause. So either the governor or security admin can call this. So what this will do, and we'll see in the other contracts, is the other contracts have a modifier usually, or a call out check just to check whether the protocol is paused. And if that's paused, then none of the functions work. Then we have a contract specific pause. So let's say, for some reason, even though the pool delegate is a trusted actor within the system, actually, let me maybe clear out some of these so it looks a bit less messy. But yeah, let's say the pool delegate for some reason goes rogue. Maybe we just decide to pause the pool manager contract, so they don't have all the functionality that they would. So yeah, that's what set contract pause lets us do. And the way that the function specific pause does is it's kind of like a negation, the opposite. So we would pause the contract first, and then we would pass in specific function signatures to unpause. So all the functions are paused on a contract, and let's say we want to unpause the upgrade functionality because we want to upgrade the contract ourselves. This is how we would then unpause the function. So the way this works in practice is if we go to is function paused, where else is this used? Is protocol pause. Yeah. So this is where the check basically happens. So first it'll check if the protocol is paused or if the contract is paused. So if the protocol is paused, it'll return a true automatically. Otherwise, it'll check if the contract is paused. If not, then it'll check if the function is not unpaused. So that's kind of like how it's doing this all this one check in one function, basically. So yeah, that's how it's being managed. And if I show you an example now on the pool manager that I was talking about. So this is the pool manager contract. You'll see we have this revert if paused, check when not paused modifier. So if we go there, you can see it's checking is function paused and passing the function signature. And then it'll do that check first to see, oh, is the protocol paused? Return true. Is the contract paused? Return true. If not, is the function specifically unpaused? Return true or false based off of that. This modifier you'll see across our protocol and all our implementation contracts. All right, so far so good?
Yes.
All right, awesome. One thing that I think is really cool that I just remembered that I want to show you as well is how we actually initialize proxies. So I was at the DeFi Security Summit at ECC, and I won't name who, but yeah, they were talking about how to initialize proxies and what's the best pattern. But they didn't mention this pattern, and I think this pattern makes the most sense. So if I go into our submodule and go to the pool submodule, so we have this folder called proxy. So this kind of helps us manage our proxy. So this is the pool manager contract. So first thing you'll notice is we have a pool manager storage contract. So we don't actually, on the implementation, keep any storage variables. We keep the storage variables in a separate contract that we inherit from. And this way, because in proxies, you want to make sure you're always overriding the right storage variable. You don't want to accidentally hit the wrong storage variable. So say we implement a new version of the pool manager, we would inherit from the same pool manager storage. And let's say we want to stop using a specific storage slot. So we would, maybe deprecate a storage slot. So we could mark something as deprecated. Actually, let me find an example of something we've deprecated so you guys can have a look. So this should definitely, So this is for a Maple loan, so a fixed term loan. So you can see we're using the same storage pattern. So we've got all these storage variables. And you can see we've got this storage slot for claimable funds that's deprecated. So when we upgrade, we can just rename the storage variable to have deprecated in it, so we know we're not using it anymore. And any new variables we add, we just add to the bottom continuously. So that way, we're managing our proxy storage properly. So going back to the pool manager, that's what this is doing here. Another cool thing we do is we have a separate initializer contract. So how does this work? So if we go back to the pool manager, as part of its the deployment process, we usually call this migrate functionality. So if we go to the factory, for example, so when we create an instance, so there's multiple levels to this, as you'll see. So if you have any questions at any point, please do say. So we have our own Maple proxy factory. So in our proxy factory, when we create an instance, so if we go to create instance, so we create this new instance. But what's happening here? So if we go to create instance, it'll deploy a new proxy, and then it'll initialize that proxy. And to initialize that proxy, the factory has a registered understanding of what the initializer is. So say there's it might call a migrator contract, potentially. Otherwise, what it'll do is it'll call the initializer contract. So in this case, it's calling the initializer contract. So this is all part of the creation. So there's a completely separate contract that's being used for initialization. So let's go to this initializer contract. So you can see we're inheriting from that same pool manager storage contract. So the storage layout is exactly the same as our implementation. And then we have this initialization function. So this does all the checks, to make sure, okay, valid pool delegate, valid pool asset. And then it sets the required storage variables. So for example, it'll deploy a pool, it'll set what the pool delegate cover is. So by having this separate initialization contract to the actual implementation, we don't actually have to worry about someone recalling an initialization function. So we think that's like a super clean pattern, keeps things super simple in terms of managing proxies. So yeah, that's something that we're quite happy with as a process. All right, so we've covered how the pause functionality works. We've talked a bit about how we manage proxies, kind of gone over um, the different submodules at a very high level, like what they are. I think one of the things let's maybe go through next that we had on the list is um, how actually a question for you. It's like, what do you think would be worthwhile for the users to go next? Because we can go into how we're doing testing in our monorepo, or we can continue to go through some of the submodule contracts as a starting point, because there's quite a lot in the submodules still.
Um, let's go into testing.
Yeah. All right, let's do that. Maybe we can come back to submodules. I think how we manage withdrawals is quite interesting. But yeah, let's go into our testing suite. So
Yeah, and
just to give
Farhan,
everyone an over.
sorry,
Mhm.
could you zoom in a little bit again into VS Code?
Yeah, we'll do. All right. So in each submodule for each module that we have, so let's look at open term loan. We have tests there. These are all unit tests, and potentially some integration tests. Um, so the testing here is focused on unit testing that specific contract. So the way that we differentiate like a unit test from an integration test is in a unit test, if there's other external contract dependencies, you will use mocks for that. So you can see we've got this whole contract of like mocks that we're using. So like we're mocking like our globals contract, for example. So that's kind of like the key distinction we make with unit tests and integration tests ourselves. So yeah, each module will have its set of unit tests and integration tests if applicable. Then we'll go up a level and do the main integration testing within our monorepo. So if I go to integration, for example, so let's go to fund. So here, for example, we're doing an integration test on terms of funding a loan. So you can see like there's loan contracts here, there's a loan manager contract here, quite a lot of setup going on. So this is using the actual contract. So we're bringing in all the submodules together and doing our testing here. Yeah, you'll probably notice we're quite particular with our formatting. So yeah, we like aligning our equals and stuff like that as well.
I
We
I
have like a whole
do
procedure internal.
I do the exact same thing.
Awesome. That's good to hear. Yeah. It just helps to read things, you know.
Yeah.
Yeah, for sure. So yeah, so those are the integration tests. So that's like one level. Then we have fuzz testing as well. So fuzz testing goes, yeah. So everyone's familiar with Foundry in terms of if you pass in parameters, you get parameterized testing or fuzz testing in this case. So, but we do some interesting stuff as well. So now Foundry recently started calling invariant testing stateful fuzzing. Why is it stateful fuzzing? Because there are certain um, states that you're setting up that persist through calls. Whereas in a normal fuzz test, so let's say a normal fuzz test you have over here, uh, that's not going to be a good example of a normal one. Let's go with redeem. In a normal fuzz test, you pass in some parameters. So this is a fixed array of 3 addresses and 8 different amounts. You kind of set values accordingly. You may bound some values, and then you do your assertions accordingly. So this is kind of like the contract is set up with like one state, and then everything is asserted. Whereas with stateful fuzzing and invariant testing, those states persist. We actually also built our own like fuzz setup to kind of like give our give our system a random fuzzed starting point. This is quite similar to invariant testing. We did this as like an alternative to invariant testing as well. So what do I mean by that? So we've got this contract. So it sets up kind of like some of the key addresses for like the different contract instances. And then you can call this fuzz setup contract where you pass in the number of fixed term loans you want, the number of open term loans you want, how many actions you want, and a seed. So by actions, we refer to things like calling a loan, defaulting a loan, funding a loan, impairing a loan, where you it's like a paper loss situation. How many payments you want to happen, etc. And then you can see it kind of goes through and creates this situation where at first it creates and funds loans based off of how many fixed or open term, and then we loop through and do actions where we randomly pick an action based off of the seed. So if I go to perform some random action, you can see over here, I would either do a payment, a call, etc. So quite similar to invariant testing, but just like a different approach. And I guess the rationale for us here is we want different ways to approach the same problem, just to see if there is any gap within a testing methodology. Because you can't just rely on one testing methodology all the time. Like, unit testing alone isn't enough, integration testing alone isn't enough, invariant testing alone isn't enough, fuzz testing alone isn't enough, formal verification alone isn't enough. It's like the combination of these that help build a secure system. So yeah, that's an example of us doing some like interesting fuzzing. Let's go into invariants actually. So if you've come across Foundry invariant testing already, there's some key things to keep in mind. So I'll go over our base invariant contract first. So our base invariant contract kind of sets up all the invariants of our system. So we usually define these as comments initially up top. So it's like for a fixed term loan, like the collateral balance should always be greater than or equal to the actual collateral that's in the contract. Or, for example, in an open term loan, the calculation for get payment breakdown should equal the naive calculation that we do, like the less efficient calculation essentially, just to make sure it matches up kind of like the efficient calculation that we're doing. Or like, for example, on a pool, the unrealized losses should be the same as what's on the pool manager, for example. So we've got all these invariants that are defined. We have specific internal functions to assert each invariant. So like I was talking about, the collateral balance on the loan equals the actual collateral that the function should be returning as well. So these are different invariant assertions that we have defined. So yeah, this contract basically just has assertions defined. Then we inherit this into, so this is our basic invariant contracts. We call it basic because it's not testing more complicated things like defaults or impairments. Those are separate over here. So what you can see we do is we set up, we do our setup where we initialize handlers. So you guys might already be familiar with handlers, but handler contracts are basically important to help the Foundry invariant test suite understand how to hit your contracts. So usually what would happen is if you just initialize your contracts and allow Foundry to just hit your contracts directly, there would be a lot of reverts. And if there are a lot of reverts, it's not really that useful because you're not really understanding what your system is capable of or is doing. It's just like, 10,000 reverts is not going to tell you anything. So you kind of want to make sure your system doesn't revert. So you define specific handler contracts. So for example, this fixed term loan handler, what this does is it's got functions on it like create a loan and fund it. So, the right sort of like input variables get sent, or it's got a function to help make a payment. So, making sure like the right person is calling it, they've got enough funds to make a payment. Or to impairment make payment, that's a separate one. Or to impair a loan, for example, where you kind of solidify a paper loss. So like these are the functions that would get hit basically now by the Foundry invariant test suite, as opposed to directly calling. If I go to Maple Loan, so they'll have an impair loan functions or impair function somewhere. What it's called? It's just called impair loan. Or default. I haven't opened this contract in a few months, so bear with me. Impair. Here we go. So yeah, this would like impair a loan, for example. So yeah, this helps us basically kind of like obfuscate that, not obfuscate, but like abstract that away. Sorry. and make it super easy for the fuzzer to hit the right functionality. So these are the handlers. So going back to the invariant test suite, so you can see we set up a handler. So we set up one for like liquidity providers, one for fixed term loan, and then we've got something going on here with what we call a distribution handler. So this is something that we've developed in-house. We do want to work with the Foundry guys to see how we can like work on this together. So one thing to understand about the Foundry fuzzer is it has a uniform probability distribution of all the contracts that it hits. So let's say you define the target contract as all those different handlers. So the LP handler, the fixed term loan handler, etc. So now let's say it's got 2 target contracts. Now, because there's 2 target contracts, 50% of the calls will go to each of the handlers. Now, this might be okay for most people, but if you've got like a big system like ours, there are certain handlers that get called very rarely, or specific functions that we don't expect to be called a lot. So of course we would do like a test where we kind of like don't define these distributions as well, because we want to make sure that it catches any edge cases, but we want to kind of see how our system is behaving in like a normal sense. So what we've done is we've defined this contract called a distribution handler. So if I go back here, you can see the target contract is this thing called a distribution handler. So what is this wonderful thing doing? So this contract will get 100% of the calls now. So when we initialize it, we pass in what the target contracts are and what the weight of each target contract should be. So we define the weights as a sum up until 100 as a total. And then what essentially we do is this is the only external function that is called within this distribution handler. So what this does is it basically, based off of the seed, calculates which contract it should hit. And essentially we're doing this by looping through and just figuring out what is that number between 1 and 100, as we defined over here. And if, say, the target weight of the first contract is 20, if it's any number between 1 and 20, it'll hit that first contract. If the second contract is then 21 to 100, it'll hit as if any number comes and it'll hit that second contract. So the assumption here is as the number of calls you hit the distribution handler trends to infinity, the probability distributions should match the weights that we've defined. So it's super important with this actually to make sure you have a high number of runs in depth to just make sure that the probability distribution matches like what you're setting. So far, so good.
Yeah, this is really cool. Yeah, it would be awesome to get that integrated into Foundry.
Yeah, because essentially what we want to be able to do is just say, hey, for this handler, for this function, we want to hit it 30% of the time. Or, for this function, we want to hit it 25% of the time. So you can see here when I'm defining the weights of the 2 handlers, the first handler is 20%, the rest is 80%. And that's how then it gets inputted into the distribution handler. And the way that we kind of then manage that on each handler is we've just got one function in each handler called entry point. So let's go to the LP handler, for example. So they all inherit from this contract called handler base. So let's check out handler base, what it has. So it has this function entry point. So whenever the distribution handler is hit, it hits then of the handler contract the entry point function. And then the entry point function figures out, so it calls this address with the specific selector. And we figure out the selector again as a similar concept. We go through the weights, and like when you set up a handler in its constructor, a part of what you're doing is actually setting up the weights as well. This function might be hit, for example. That's part of the process. So if we go back over here, so you can see, we're setting the weights. Sorry, it's not in the constructor. It's in, there's a specific function called set weights, which I believe is on the base. Yeah, over here. So you pass in the function signature and the weight. So yeah, that's how we're basically doing the probability distribution handling. Now we know, okay, these are our handlers we've set up. These are like the specific like distributions we expect. then we assert the invariant. So, we kind of try to optimize this because for some we need to like loop through and get certain parameters and pass them through. For some we can just call them directly. As if I hide this, so you can see we can just call specific assertion functions directly. Um, and that way we just assert our invariance. And as if you know with Foundry, the way that it's working, it's asserting it before a call and after a call, which is technically the same to a large extent. And that's how the invariant test suite then runs. So we can see for each set of contracts we have our invariants defined that are being asserted. So that's the TLDR. I believe in a previous podcast you already covered some other quirks like how you need to handle time within the invariant test suite. You actually have to manage it yourself. So this is something, we have functions like to use the current timestamp and warp it accordingly. You can see in each handler there would be a warp function somewhere. Does this one have it? Maybe not in this one, maybe in our fixed term loan. It might be in handler base actually. Yeah, there we go. To use timestamp. So, we take the current timestamp from the contract, do our function, and then warp or set it accordingly. And then sometimes warp randomly as well. Where is the we're warping within our functions here. Here's an example of a warp function. So randomly, if this gets assigned as a function selector, then it'll just warp time. Because with loans, you need to do the passage of time, so interest gets accrued and like loans come due. So that's important for us to manage as well. All right, that was a bit of a mouthful with invariant testing. Any questions?
No, this is great. So I've been looking into invariance testing, the weighting mechanism. I think you're the first to do it in that way, right? I've never seen that before.
We've not seen an example in the wild. Maybe someone else has done this, but we definitely came up with this specific implementation ourselves.
No, that's super, super dope. I just feel from a Foundry point of view, I still feel like there's still a lot of boilerplate to do invariance testing, but I'm pretty sure that's, it's still a pretty new feature and stuff. I think we'll figure this out in the future. It's gonna be better in Foundry, I think.
Yeah, I mean, it's like when you're unit testing, like maybe you're unit testing an internal function. Now suddenly you need to create a harness, right, to be able to interact with that internal function. It's like a similar mentality here with the handlers. It's like you're creating a harness to interact with your contract in a proper way, in a way that you'd expect it to kind of behave as well. So that's kind of like my mental model of thinking of it. So I think it might be hard to get around that specific kind of boilerplate, but maybe there are ways we can kind of abstract away some of the other nuances, like managing timestamps or the probability of functions being called and things like that. That I think we can definitely simplify. Yeah, for sure. All right, so that's invariance. Another cool thing that I wanted to talk you through actually is, so now we've deployed our protocol, or we're in the middle of deploying our protocol actually. So let's say, we're in the middle of a deployment. How do we actually make sure that what we're doing makes sense? So there's a couple of things we do actually. So one thing I'd like to introduce is what we call a validation script. So let's say I'm deploying a contract on mainnet, and I've deployed it from my current repo. Maybe I want to check that the code hash matches. So this is what this first example with deploy contracts is doing. So we run our validation base. So here you can see we're creating a fork basically. So let's say you've done a transaction on a Tenderly fork just to test your deployment. So you deploy a contract. So we would pass in the ETH-RPC URL as a Tenderly fork. And then what we do is we can validate a contract. So then we can pass in what's the specific implementation and the expected code hash and check, hey, in this deployment transaction that we just did, does the implementation we just deployed match the code hash we have in our code base to make sure we're deploying the exact same version and like no one's gone in and changed any of the code, for example. So you could just run this as a uh, as like a script. So the way that we do this is, let me go through our make file here. So our make file's got all these like helpful commands, and you can see we've got this like validation script where we basically run this forge script command validate. So these are script files with the .s notation. So yeah, they're not like tests per se, but they're scripts. So usually scripts are for like deploying and doing mainnet transactions, but you can also use scripts to validate contracts on like mainnet or forks as well, without having to do it via test. You could argue you could do this via like a test as well, but we just like doing them via scripts. So yeah, it just runs and validates like the code hashes here. Now, let's say we want to validate an upgrade that we've done for our globals. So let's say we're upgrading globals, we're calling set implementation on the fork or mainnet. So we would then run this script where, hey, so this is the current implementation, and we expect that the implementation matches the contract we just deployed. So this is coming from our address registry. So yeah, it just checks, hey, the new implementation matches the one we just deployed. Or another one, for example, we set a lot of keys in our global. So like, what the specific factory is and like the key associated with that. So you can see we're doing these requires where you can run this script again using forge script. And it just checks that on that fork or mainnet, specific functions are being set. So the way that you can kind of imagine this is, if I go down here, is so let's just say this is like the passage of time. So we run transaction. So this is the first transaction we want to run, T. What we would do is so this is the passage of time on mainnet. So we would fork mainnet at this block untenderly. We would then run transaction 1, and then we would run our validation script on the fork. So we run our validation script. Now that we've run our validation script and it passes, it's like a green check, we can then run that transaction on mainnet. So we run transaction 1 on mainnet, and then we run the validation script on mainnet, and then it passes. Then we do the same where we fork again for transaction 2. We run transaction 2 on a fork, run the validation script, it passes, okay, good to go. Then we send the transaction 2 on mainnet. So I think you're getting the idea. But that's essentially kind of like our deployment procedure or configuration procedure from any mainnet operation. So it's like super double checking that everything is being set and done properly, because like a key issue that a lot of people tend to run into is like configuration on mainnet, or sending the wrong parameters, and then suddenly things aren't set up properly and things can get borked. Sorry, I think you have a question.
No, even in audits, right?
Yeah,
A lot of times the deployment script isn't audited, which
yeah,
brings a lot of issues, right? So yeah,
exactly. Yeah.
this definitely makes sense. It's like a sanity check for yourself, to make sure I'm deploying the right things.
Exactly. And not just deploying, but configuring as well, which is
Okay.
super important. So like
Yeah.
we actually then we get our deployment scripts now also audited. Like, so that's like an important part for us as well. And like any procedure that we're doing, like, or either we write like a super clear test or document it. So like the auditors can check, hey, this procedure makes sense. And then also the other cool thing is, so operationally, when we're actually doing our deployment procedure, we usually have like a checklist, like a Google sheet of checklists of things we need to do. And, the whole team is actually running these validation scripts. So we have redundancy in the operation as well. So so say I'm sending the transaction, I then run the validation script, and then my team members also run the validation script. So you need a thumbs up from multiple people to say, yes, this transaction that just went through is correct and expected, like the output. So it's like you've got that redundancy operationally built into the process as well.
Mm.
And I think I haven't heard a lot of people talk about the operational side of things, which I think is like equally as important as also writing secure smart contract code as well, right? Super important. So yeah, these are examples of our validation script. You can, go into our repo and have more of a look. But yeah, we think that's like a super important process. And then there's one last thing we do as well, which is more applicable to our protocol, but like other people that have like a complex protocol as well, might be useful to do as well. We call it a validation lifecycle. Um, so what do we mean by this? So remember I went through that fast setup where you can create like multiple contracts, multiple loans, fund it and do these random actions. So we're utilizing that for this validation lifecycle script, we call it. So when we deploy a pool, so let's go down to like the last one as an example. So let's say we've done all the transactions now. We run this validation lifecycle. So in this case, it's just adding loan managers as that was like a separate operation. It runs this validation lifecycle for each pool. So this is like the Maven permission pool. It passes in all the loans, the seed. And what this does is now that all the mainnet operations and upgrade is done, it does all the operations. So it creates loans, funds loans, impairs loans, defaults loans, et cetera, randomly. And this is like another sanity check to make sure, hey, now that we've deployed and upgraded our protocol, or we just upgraded our protocol like we did on our recent release, because it was already deployed and we were just upgrading contracts, that everything still behaves the way we expect it to, which is super important. So this is actually the last validation step we run. So when we're doing a deployment, we're doing all these validation scripts, and like one of the last ones is this life cycle, where then we basically check that everything runs the way you expect it to. It takes like 2-3 minutes to run because it's quite a lot going on when you're running like a whole protocol's actions. But it gives us confidence. Hey, we can go to sleep at night knowing our protocol works the way we expect it to.
Mm.
Yeah. All right.
That's very cool monitoring. And a great CI/CD pipeline. I think that's a good analogy before deployment.
Mm, exactly. I guess so the other thing to go with like operations and deployment is we have these what we call health checker contracts. So let me go over the protocol health checker contract. So you can see again, this might look familiar, the invariants that we defined. So these are separate contracts where we basically have these deployed on mainnet, and we use Tenderly with their Web3 actions to ping these contracts. As you can see, it's got the struct of bools for invariants, right? And what happens is this check invariance function is like pinged every block, basically. So we pass in like a pool manager address because we have multiple pools. We have to do it separately per pool. We basically ping this, we get back this struct, and we check if any returns are false. Because if anything returns a false, that means an invariant has been violated. And if that happens, we automatically get pager dutied, and it's you wake up in the middle of the night, hopefully not, knock on wood, uh, and then maybe you need to go trigger your circuit breaker or something. But this is also like super important, where we kind of like check, hey, all our invariants of our protocol hold true, and all these invariants are like are similar to what we've kind of discussed previously in our invariant contract, like this base invariance. We just like copy them over, make these requires instead of asserts, or like we have like this Boolean logic to check, whether it's holding true or not. And so it's actually not required, it's Boolean logic, like greater than equal to whatever, to just check, is this invariant being held? So we have to write these out slightly separately because we can't use assertions, because that's like a testing thing specifically, not for mainnet. And then we have this checked constantly as well. So you can see there's a lot going on here in preparation, deployment, and action, like on-chain operations, and then monitoring afterwards as well.
And you do this for every block?
Yes.
Oh, okay.
So all invariants are checked every block, and we make sure that everything holds true. Otherwise, yeah, we'll get pager dutied, which we don't want to happen. So,
Um, okay, so if one invariance breaks, um,
hmm.
you actually want to take a manual look at it and not automatically do a circuit breakers thing and stop the protocol.
This is a good conversation point. Because I know other people are like working on circuit breakers, and it's there are people out there that are building products to kind of automate this. Um, we've had like an on and off thought about this. So it's like, what if there's something wrong with like the invariant contract, or what you think is an invariant actually isn't an invariant? So we had an example of this back in December. So we just launched the new protocol. This is what I've been showing you in December. Uh, and yeah, we had the invariant contract out on mainnet, and it was checking. One of our invariants was basically you can never have a zero interest loan.
Hmm.
Whilst business wise, maybe, in reality, the protocol does allow a zero interest loan. You just set it to zero, right? The interest rate. Um, so we were actually migrating a separate loan, and as part of the migration, we had to set the interest rate to zero.
Hmm.
And then suddenly we had PagerDuty go off, and we're like, shit, what's going on? And then we realized, we were doing the migration. We set it to zero interest rate. This is
Hmm.
fine. This is okay. Now, in that case, if we had an automated circuit breaker, it would have just paused the protocol, and and now suddenly we can't do anything till we unpause it. It's also kind of like a bad look as well if you kind of like, suddenly your protocol's paused, the external actors can't do anything, your LPs are suddenly like, hey, why can't I take my funds out or whatever? Um, so you have to be quite careful with it. So yeah, it's not an exact science. We're definitely leaning more towards a cautious approach, but we don't know if the answer is automating the circuit breaker. But this would be a
Hmm.
good way to automate it with. But you would need to be 100% confident in your invariants, like that they will
Yeah,
always hold true.
you're afraid of false positives, which is
Exactly.
understandable. Um, yeah, maybe it's a time thing. So maybe after, okay, 6 months to a year or something where nothing happens, you are more confident in your invariance testing that you start thinking about, okay, maybe I can automate this. But
Yeah,
yeah,
potentially.
yeah, false positives are if you break on a false positive, it's a bad look for sure. That's definitely
Yeah.
true.
Yeah, so we only had one false positive. That was the example that I showed you, and then we updated our invariant contracts accordingly. Knock on wood, nothing has worked since. Yeah, because we have to update these contracts with every new release as well. So, for example, when we launched the protocol in December, the new version, it only supported fixed term loans, and we just did a big launch in the start of June to support open term loans. So you can see, like, we have separate invariants now for open term loans and like a separate health checker for open term loans because it's got different functionality. And then we have to kind of update some of the other health checkers to kind of accommodate this as well, right? Um, so yeah, it's the Lindy for your health checkers gets reset basically.
Mm,
Uh,
yep.
so yeah, there's that element to it as well.
Awesome. Let me take a look at our list. There is still the bytecode check left, which
Ah, yes. Let's do that. So, contracts called equivalent. So, just to give you context, so we were doing a new release at the start of June for open term loans, but we wanted to kind of show our auditors, hey, we want to prove to you that we have not changed any other functionality of the other contracts that we don't change. So, for example, the pool contract wasn't touched, the delegate cover wasn't touched, some factories were not touched, and we want to prove that. So, how do we do that? So we to set this up, we basically create our control versions uh, from our modules because the modules we're still importing, right? So if the withdrawal manager that's deployed on mainnet and the module that we have here are the same, how do we prove that? So for example, we take the withdrawal manager here, and which you can see just to show you the import to prove it. It's coming from the withdrawal manager uh, module contracts withdrawal manager.sol. So we want to prove this withdrawal manager is the exact same. All right, cool. So that's first step. We create the control contract here. Now that we've got it, how are we doing this? So to test the equivalence, so I go down here. So we want to basically check that the code hashes match. So if we hash the code, that they should be the same of what's been deployed and what's local to us. So the control, which is the local, and what's the implementation out in the wild. So this implementation address is coming from our address registry. So this contract we're inheriting, that won't show it there. But yeah, it's basically an address coming from there. So what we do is you have to remove the metadata hash.
Mm.
Why do we remove the metadata? Because as part of like post deployment, maybe we change a comment on the implementation just to make it more legible locally. So for example, this control withdrawer manager, if it's got any commit changing any small thing like a comment, an extra, anything like that, it will change the metadata hash. So that's why we just strip out the metadata. And the way you can do that is, so there's specific opcodes, like the invalid opcode, and usually, so you can check the Solidity documentation. There's an opcode that kind of starts where the metadata is, and then the metadata usually has like A2 and 64 with it to kind of denote the IPFS hash. So you can kind of loop through your bytecode, check the specific opcodes where they are, which will be towards the end of your contract, and then just strip them from your code, basically. And then just get the code without the metadata. And then we can just hash it, which is the same as code hash, but of course we have to do it manually because we just stripped out the metadata, so it's not the same code. And then, yeah, we can assert that it equals the same.
Mm. This is also something I've not seen before. This is also really cool. Okay,
Yeah,
remove
there's
mate.
different ways to go about it. Like if you have like linked libraries, I don't think this procedure works in. We don't actually use any linked libraries, so because then I think this rule might not hold true. So you have to kind of be careful and kind of know for sure what your code is doing. But this works for our use case. Yeah,
Mm. Awesome.
nice.
Okay.
Uh,
Yeah, I think we touched on everything we wanted to. If you have something else, I would love to look at it. If
just
not,
thinking what might be useful to go through. I mean, we didn't touch the pool contract, which is kind of like the main entry point. But yeah, this is just the standard 4626 implementation. So we inherit from the ERC20 and then implement the 4626 functions. So actually, this is a known issue with 4626 vaults is if someone front runs the first deposit, they can manipulate the shares and basically make the other person, the first depositor, lose money. So then, yeah, the way that we kind of deal with this is we define this bootstrap mint amount so that the first depositor always ends up burning a certain amount of their shares. So that kind of stops basically that attack vector. So that was our kind of way of dealing with that. So you can see with deposits, if we go to the mint function, not this mint function, the overridden mint function over here. So yeah, if the total supply is 0 and the bootstrap mint is not 0, it will then mint to the 0 address that amount.
okay.
So that makes sure that then the first depositor, who's kind of front running the initial front depositor, doesn't actually lose any funds.
Maybe one downside here is that everyone else would pay gas for it forever, right? For the check.
Yeah, I mean it's not like too terrible
Yeah, it's not a
because
lot. Yeah.
yeah, yeah. So but the security warrants it. And most of our users are institutions, so yeah, we would assume they're okay with gas costs.
That's a good point. That's a good point.
Yeah, you know, I would rather, I think they would rather pay a bit more for security, you know. So
Yeah, yeah, $2 more is okay for institutional actor. That's a good point.
yeah, I don't think this is $2, maybe like 10 cents, but yeah, yeah.
Yeah,
Every little helps, right?
yeah.
Um, so that's the pool contract. The other thing that we touched on it, but we didn't really kind of show how it works, which I think is interesting, is the loan manager and how it manages the issuance. Um, so I'll go through the example of the open term loan manager. Actually, let me close the rest and just open this up. So this is our open term loan manager. So I just kind of want to show you through fund when you initially fund a loan, how do we set it up so this loan manager knows what the assets under management is. So just to pool manager. So the pool manager is, so if I go and open up a pool, so I want to show you the whole contract flow. So assets under management, or total assets actually is what it'll be, total assets. So if I find this function, so total assets is queried from our pool manager, which returns the total assets. So if I go to total assets on the pool manager now, the way that this is calculated is it basically loops through each loan manager that is connected to a pool manager. In production, these are two contracts, one for fixed term, one for open term, and it checks each loan manager's assets under management. So that's how it's kind of checking what are the total assets in the system. So let's then take a look at how total assets under management is calculated. So this is a combination of what's the principal that's been given out as loans, any accounted interest, and any accrued interest. So accounted interest and accrued interest, it's another way of just saying, we're basically using a linear graph for this, similar to kind of like what I was showing up here. And you can think of the accounted interest as just the y-intercept. So every time someone makes the payment, maybe this linear chart moves up, and that's just I'm sorry, not when they make a payment, when say there's two loans in the system, and one loan takes an action, you still need to account for the accounted interest of this other loan and just like move up the issuance for this chart. It's probably a terrible explanation, but yeah, essentially it's the y-intercept of our linear chart, and then the accounted interest. So this accounted interest is this nice little function of get issuance. So it just calculates based off of the issuance rate that we were talking about in the interval. So the issuance rate being, tokens per second. So tokens per second times seconds gives you the tokens, i.e. the issuance. So how does this get all set up in the contract? So when we fund a loan, we figure out what its principal is. We prepare the funds. Like we by this I mean we get the funds from the pool contract. We update the principal out, and then we do this thing called add payment. So add payment is basically we initialize this struct within the storage that has any fees associated with it, what's the start date, and what's the issuance rate. So now that we have the start date and the issuance rate, we know, hey, if the loan started today at this time, tomorrow, based off of this issuance rate, I know if it's 1 day ahead, in 1 day, this is how much interest I should have accrued. So it's got its own internal accounting separate from the loan itself, where it figures out what the issuance rate is. And that's kind of like how we're smoothing out that the issuance curve there. So there you don't have that like abrupt, hey, this is interest that's paid into the pool, or hey, this interest paid into the pool. Another way of looking at it is other vaults. So like if you take a Yearn vault or something similar, they have another mechanism called slow release. Slow release is when a known payment has come in. Someone's paid 1,000 $1,000 for whatever strategy or anything. And now let's say the slow release is set so over 2 days that $1,000 gets paid out to all the token holders of the vault. That was like another mechanism that people use. We were looking at that mechanism, but we were like, but then people have to wait that extra time for the slow release to get their funds, which isn't desirable for institutions, especially. So yeah, this was the mechanism we came up with where it's like, okay, we calculate what the issuance should be for each loan. We be as conservative as possible, so we don't account any extra fees or anything like that into this. Um, and it's just the minimum amount that we expect to come in from each loan, basically. So that's kind of like the TLDR. But yeah, the loan managers, I would say, are the most complicated contracts within our system because yeah, there's a lot of accounting going on, and there's like lots of different edge cases to account for. Like it helps refinance loans. This claim function is like the main entry point for a loan. So whenever a loan pays in a loan, a claim function is called on the loan manager to then update the accounting on this loan manager before it then sends funds into the pool. So yeah, that would be this is kind of like the core accounting of the system. So I thought, yeah, if I don't at least go over this at a high level, then you've kind of missed the main chunk of Maple.
I always ask this when I see it. Why require and not custom errors?
Oh, good question. We just think required to read better. Um,
Hmm.
I don't like the whole notion of, if if condition, then, revert. Um, I yeah, I know you can in like you can either have it in the blocks or not. You can have it all in one line. Um, but yeah, we think requires just read better, and having the verbose strings is actually super useful for our off-chain team, developing like the front end and like the subgraph, because then when they're testing, they can clearly see, oh, this is the loan manager contract, this is the claim function, and the issue is invalid borrower. So that's kind of like our nomenclature. Like you abbreviate the contract, the function, and then give the error. So it's super
Hmm.
useful for their development. Otherwise, they need to search up on some table, the 4 bytes of what the custom error is, and figure out, oh, okay, it's this one, and yeah. So that's why this is our preference. But I
Okay.
also appreciate like custom errors can be cost efficient, assuming they don't have parameters more than one parameter, um, because otherwise it is still taking up the same space. So yeah.
Yeah, and smaller bytecode as well.
Yes, this is true. Strings do add to the bytecode. We have ran into that issue a lot, actually, where uh, we actually have a custom CI script to check our bytecode limit, so it'll tell us if we go over the limit. Because yeah, we ran into that a few times.
Okay, okay. All right, Farhan, this we are at 1 hour 50 minutes. I could go on, but I think that's a good time to stop. Um,
Yeah, let's give viewers something to go check out as well.
yeah, this was super, super interesting. So I learned a ton today. I think every smart contract dev has like a few repositories as a reference point, if you need to check something out. Maple Finance is one of mine now. Uh, so really, really interesting stuff, especially the monitoring after deployment stuff. I will definitely copy some things over to Dia, the project I'm working on. So yeah, thank you for this great presentation, dude.
No worries, it's been fun. And yeah, any questions that your viewers have or you like, feel free to reach out. We're always happy to chat with folks.
Awesome. Yeah, you can. I think the best place to find you is on Twitter, right?
Yeah, 0x Farhan is my handle. So yeah, feel free to add me and yeah, we can chat.
Awesome. So I'm gonna link Farhan's Twitter, the repository, Maple Finance, of course, in the description. Farhan, thanks again for taking the time, and I will see you guys in the next one.
All right,
Bye bye.
take care, everyone. Bye.
Bye.